I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined, as always, by my co-host, Taylor Sparks.
It's great to be here, and it is a really great episode of the show. I'm so excited, and I'll tell you why. For the last 5 years, I've been diving down the rabbit hole of generative AI for new materials. It has been so exciting. It's something I've put a lot of effort into, but there was a breakthrough earlier this year from Microsoft. So we're actually going to hear it right from the horse's mouth. Okay, with that said, we are joined today by Tian Xie of Microsoft. Tian, you are somebody who I have known about for a long time. We run in the exact same circles. We have the same research area, and yet I don't think we've ever met in person, which is mind-boggling. So I am just delighted to have this conversation today to get to know you a little bit better and to talk about what is looking like your sort of magnum opus, which is MatterGen right now. You want to do a quick introduction?
Yeah, absolutely. So hello, everybody. So my name is Tian. So I'm a principal researcher and a project lead here at Microsoft Research AI for Science, where here I lead a project which we focus on building some of the foundational AI capabilities for materials design. So my researcher, as Taylor have said, mostly focused on MatterGen. And then we have another colleague in Asia, Zihen, who leads the MatterSim effort. And Taylor, again, it's the same. I really have been like hearing your name for a really, really long time, and I've been like constant listener of this podcast. It's so great to be here, finally speaking with you, and so nice also to speaking exactly about the topic about generative AI for materials.
Yeah, absolutely. Well, maybe to set the stage, we're going to get into generative AI, but this is really a story about materials discovery. And materials discovery, I've said many times on this podcast, is the concept that got me pulled into material science. It excites me to no end. And so tools that are aimed at that are just really great. Maybe before we talk about that, we mentioned the traditional pipeline of what's been done in the past and what the sort of modern state of the art is. And I guess most listeners know that the way that we've discovered materials in the past has been trial and error. It's been following a hunch. It's been sort of using maybe at best empirical methods like simple relationships that we observe. And the problem is that this has been really slow. Have you ever been an experimentalist at some point in your career, Tian Xie? Have you actually tried to be in the lab making things one at a time by hand? Because that's where I cut my teeth. I was not a computational guy, and it's a lot of work to spend that time actually trying to make materials, and it's pretty disappointing the rate at which you get it wrong.
Yes, actually, I do have a 2 year experience in my undergrad. So I was like growing uh, physical vapor deposition
Okay.
(PVD), and so I'm trying to grow some 2D materials. So which is a very exciting research topic at that time. So and then I switched to computation at the beginning of my PhD. So from a experimentalist. So part of reason that I got super excited about computation and AI at that time was really exactly as you said. It's so slow to do everything right experimentally and trial and error. So and the computation seems to be much faster. And also at that time, actually, when I started my PhD, so it was exactly the time when AlphaGo
Oh yeah.
first
Okay. Yep.
came out, and it kind of beat the world champion right in the Go competition. So that got me thinking. Okay, so if so Go is a area is a game that people just develop their entire career, right? Trying to perfect your understanding of the Go and also build a lot of intuition over how would you make the right Go move. From that point of view, it's actually kind of quite similar over how experimentalists design
Totally
new
is.
materials, right? So therefore, that really got me thinking. Okay, maybe this is a thing that going to change how we design materials. That's exactly the reason why I started to focus on my PhD. on ML4 materials. That was in 2015. And then, then here we are.
Yeah, a perspective that somebody pointed me towards was this great article. It's worth a read. It's called Birds and Frogs by Freeman Dyson. And it basically relates two different types of approaches to science. You have frogs, which in nature are very close to the ground and fairly limited in terms of the range they can move, but no leaf or twig or even depression in the earth really escapes them. So while they're not moving particularly fast, they have a very strong grasp of that local environment. And then you can contrast that with some scientists who are more like birds, where maybe those depressions in the earth or those individual details of leaves and twigs aren't necessarily at the forefront of their mind, but that they can grasp a lot more or a larger and wider area. And when I look and think about the experimental world versus the computational world, I see a lot of similarities there, where many experimentalists know their niche very well, probably better than any computational algorithm will be capable of knowing that very specific niche, but their range in terms of how the vastness of space that they can explore is maybe a little bit limited.
That is super interesting. Yeah, exactly. So I was recently, I was actually last week, I was listening a podcast that was kind of talking about the human evolution, and it was kind of making a argument that actually, because there used to be different kind of human species besides us, Homo sapiens, and then they say that part of the reason why Homo sapien are becoming the only dominant human species is because humans are much better at collaborating, and so they specialize into individual domains. So that even though Homo sapiens is not the collaborationist, they actually end up becoming the dominant. So there's kind of trying to say now all the language models, they are all the generalists. So therefore, maybe in the future, people could look into is a lot of specialized models that was kind of orchestrated, organized into a society of AI agents. So that's interesting.
Very cool. So this pathway towards materials discovery started with just try stuff. That evolved to try stuff with some trends that we're observing, very simple, low level empirically. And then that evolved in my career like 10, 12 years ago to data-driven tools, which is the same thing as empirical models, but in higher dimensions, higher fidelity, more complex models, but it's the same thing. The concept here is let's learn from examples we've seen before, but using machine learning tools, we can find patterns in data that would be very hard for a human to capture. Once you have the ability to find and leverage that pattern, you can use it to do things like screening. In fact, we just did an episode with Microsoft. Episode 88 was about accelerating materials discovery with Microsoft, which really was a screening effort. The power here is, vastly better than what humans can do alone. So it is an exciting technique. But the sort of nagging criticism that at least I faced when I was talking about this type of approach over the last 12 years was people would say, I'd say, hey, we've discovered this new material, right? For super hard materials, we had some and things like that. And a critic in the audience would say, you didn't discover anything. That material existed. You just found out what it was good for in an efficient way. And honestly, that's a true statement. I couldn't disagree with it. True materials discovery means that you're going beyond the list of known materials. And to do that, we hadn't, up until very recently, had those tools available. In fact, I think it was around COVID, at least that's when I got pulled into this space, when Gen AI, and your regular listener probably first encountered Gen AI with things like ChatGPT or DALL-E, right? But all of a sudden, you can do things that don't look like linear interpolations between two data points. They look like it's extrapolating out to really new things. And that's the concept of Gen AI. Aimed at materials, what does that look like, Tian?
Yes, exactly. So basically, I think you summarized this perfectly. So basically, there's a huge amount of effort right around creating these computation workflows to screening new materials, and so at Microsoft we have our Azure Content Element platform, which really allows you to screen this super fast at the cloud scale. But this only allows you to find materials for with a specific property, right? Given a existing fixed set of materials. So you're not discovering new materials beyond those fixed set. So what Gen AI, what a generative model allows you to is really to go beyond that. You can directly starting from a property that you're looking for, and the model would be able to generate candidates, and a significant portion of these candidates will be novel materials that people have never seen and discovered before. and then this would satisfy the property that you're looking for. So I think that's the big improvement these Gen AI models that begin to enable.
And it took a little bit of time to get there. I think some of the first generative models that really kind of started to gain prominence were generative adversarial networks, or GANs. And these were just based on the principle of you have some sort of generator model, and then you have a discriminator that tries to determine real from fake. And in competition, you slowly start to improve the generated candidates. But then these started to evolve as well into things like variational autoencoders, where now all of a sudden we're taking candidates that we know, we're compressing them down into some latent space, and then recovering them, and you can then sample from that latent space. And then diffusion models came about. I'm glossing over some important incremental steps between those, but diffusion models are kind of the how to describe it. Diffusion models are kind of the best in class right now for these sort of generative tasks. And the idea is very, very interesting. And that's in some part the foundation of MatterGen as well. So maybe now's a good time to transition to a little bit how those work and how those are being applied in MatterGen.
Yeah, absolutely. So first, the diffusion model is a class of generative model where the core concept is quite simple, right? So you take one of your data, it can be an image, it can be a material, and then you iteratively add noise to that data. And then what your neural network, what your model do is to learn a denoising model, which would be able to denoise this the corrupted data into the original data form. So once you trained your diffusion model, the score network with a lot of data, right? So then by just taking a random corrupted image, which usually started with noise, a completely random noise, then you would be able to generating novel images or novel materials. So I think the most powerful thing of a diffusion model is that it is a very flexible framework because this concept of adding noise and denoising it is very general. So which means that you can then apply this into different kind of data modalities and materials. More specifically, crystalline structures is one of them. So I think I actually doing my postdoc, right? Because it's actually quite interesting because I've been kind of thinking about this problem about building generative models kind of really for a long time because because a lot of people, because I was doing my PhD, I was working on some property prediction model was based on a graph neural network, and so there's a work that I did called CGCN, which is one of the first graph neural network specifically designed for materials. And at that time, when I was talking about property prediction models, one of the first questions that people in the audience will ask, okay, now you can go from structure to property. Can you go back from property to structure, which is the kind of the inverse problem, and many people consider as one of the grand challenges in materials design. So I've been kind of thinking about how to do these generative models for a while, but there isn't really a good algorithm that really enables to have a really really good performance, meaning like in terms of quality of that it generates. And then during my postdoc, I basically spent I joined a group in at MIT called that was led by Professor Tom Yakalai and Regina Bazalay, who specializes building generative models for drugs and biomolecules. And I learned the diffusion model at that time over there, and and that it was the time when diffusion model really first came out, and it has beginning to achieve really good performance in both point cloud generation and also molecular generation. So basically, you can begin to say that diffusion model suddenly becoming the state of art of all different kind of a task. So that's why I begin to focus on trying out diffusion model for materials. And actually, it's quite surprising that basically, I think after only 2 weeks of trying, and it immediately worked, and then it worked really, really well. And then all the previous ideas, basically, we tried many different versions of ideas, just doesn't work. It never works very well. So then the diffusion model, once you apply it, it immediately worked, which was fascinating.
I'm curious. So you guys in the past have always done crystal graphs. We and others in the field have taken some different approaches. Instead of using a graph representation, when we try and learn the structure, we take the information from essentially the sieve card. And there's different ways of encoding that. We end up using a tensor. There's other ones out there. What are the advantages of crystal graphs? They are really powerful ways for representing materials. What role does that play, or is it all the algorithm? Does the representation matter in your perspective?
Yeah, that's a wonderful question because basically there's a lot of debates regarding because now we are in an area of language models. People say, okay, maybe the model doesn't matter,
I'll
only
tell you,
the
I've
data
jumped ship,
matters.
man. I've jumped ship. I'm like on team language model. I when I first heard of this, it was Luis Antunes. It was Ricardo Grau Crespo over at, I think they're at Reading or Bath. Drawing a blank which one it was. But the point is, they told me about this, and they're like, we're just going to use an LLM to create the sieve card. And I was like, that's not going to work. Dude, it works. And that was like the very first paper. And now we've seen Meta jumped on this. My group's doing this. Like, it works really well, actually. So I've jumped ship. I'm curious if what your take on it is.
Oh yeah, I'm super impressed because I think one of their first work right is the Crystal LLM, right? So that really just to train the language model, right? That directly on SIF and that it performed quite well, which makes me very very surprised to be honest.
Right?
And then exactly so but then I think so far from what I'm seeing today that the best uh, language model, basically auto-regressive model, right? So that the generative model still performs slightly worse than diffusion model. I would say in terms of generation quality, diffusion model still works better
But they're
than generative
very
models.
close.
Yes, exactly. So therefore, I think to me, I think it's really about the data.
Yeah.
So and I would like so let's say we scale up the data up by 10 times, right? So then what model will perform the best? I don't know. So that will be very interesting to see. So I'm very optimistic about okay, yeah, I can go into a lot of details over what's the pros and cons of auto-regressive model versus diffusion model because
Hey, we can
yeah,
meet in the
basically,
middle. We could do something like
but
Mercury, which is a language model that uses diffusion, right?
yeah, exactly. So that'll be super good. But yeah, let's not go into too much details on this.
Yeah. Okay. The point is, and maybe we've spent enough time on this to say, like, gen models now exist. We've mentioned this idea of latent space, which is this nebulous term that gets thrown around. It's essentially talking about where we're going to be able to find new materials, but they're not in their form that we need them to be in that latent space. They have to be reconstructed from the latent space, either via denoising diffusion or by a VA or whatever else, right? We think we've got tools that can do that. So now comes the time where Microsoft says, let's do it. Let's actually try and find new materials. And let's try and do so in a way where it's not just sampling new for new sake. You're trying to find specific. So when we say that, what we're saying is that this is conditioned generation. You want to introduce MatterGen and how this is achieving inverse design through conditioned generation?
Yeah, absolutely. So as I said, so I think one key advantage of a MetaGen that we enabled compared with the previous model is this component which is called conditional generation, right? So previous models you can already generate novel materials, but the ability to do property guided generation it's very limited. For example, in one of my previous works, CDVAE, we can do energy based property guided generation, but when I tried something more complex, like band gaps, it doesn't really work at all. So therefore, one thing we really enabled in MetaGen is this property guided generation. So this is enabled by an approach called classifier free guidance, and so which is something it's the same approach that was powering the image generation capability of DALI 2 and other text image generative models. And then is so to enable classifier free guidance, right? We need to have a single diffusion model, which means that you have a diffusion model that is purely operating on the crystal structures, does not involving encoder, because in the CDV we used to have an encoder. Now we don't have an encoder. It is a simple kind of adding noise and denoising process. And so therefore we designed a specific diffusion process for crystals which involves three components: the diffusion of atom types, the diffusion of atom positions, and the diffusion of periodic ladders, and their domain-specific designs for each of these components. And then we learn a single denoising network for the entire model. And then this new architecture allows us to do to train a conditional model jointly. This allows to do classifier free guidance, which enabled this property guidance generation, which is for the first time we show that you can do that across many different materials properties, including chemistry, right, including electronic properties, including magnetic properties, and including mechanical properties.
So you mentioned your representation for the materials has three components. You have the atoms themselves, you have the coordinates of those atoms, then you have the lattice positions. And you mentioned that these are assembled into some sort of diffusion network. Are these three separate diffusion models that are then being joined at some layer, or is it really just one that's pulling from three separate representations?
Yeah, it is the latter. So that basically so you know that in the diffusion process, right, there is this forward corruption process, and then this reverse kind of a denoising process. So in the reverse denoising process, it's a single model, right? It's a single neural network that takes the noisy structure and then iteratively generating the stable material that you're generating. And then in the forward process, we individually, independently corrupt atom types, positions, and lattice, because this allows some design flexibility for each one of these components. And it's also the same approach used for molecular generation as well. But in the generation process, it is a single neural network that learns the joint distribution of both atom types, positions, and lattice.
Do you corrupt them differently, right? Because atom types are going to be something that's discrete versus coordinates, or if they're fractional
I was
coordinates,
just
they're
going
going
to
to be
ask
something
that.
continuous.
Yeah, that's the great question. So basically, so that's why we actually spend a lot of effort trying to design each one of these components. For example, for the atom type corruption, we use the because atom type is a discrete variable, right? So it's not continuous. So therefore, we used a discrete diffusion algorithm called the DCPM that was specifically designed for discrete variables. And then for atom coordinates, because it's actually very interesting, because for atom coordinates, if you think about an atom inside a unit cell, it is inside a periodic box, right? So therefore, if you move one atom from outside of one direction from the unit cell, and then you move it back it will go back from the other direction. So in geometry, so this kind of structure is called a torus structure. And so therefore, we designed a specific diffusion process that works for this torus geometry that is based on something called a Rep normal distribution. So that takes account of this kind of a torus geometry. And then for the lattice, because so if you kind of use the standard diffusion, then usually the mean basically of your distribution will be a zero. It's a Gaussian centered around zero, right? But then if you naively apply that to lattice, you will have a lattice parameter that is close to almost zero. Then it will lead into a very skewed lattice, and then the model will be very, very unstable, because imagine a skewed lattice means a lot of atoms packed together in a very small space, right? So this will make the training highly, highly unstable. So therefore, what we did is that we have a non-zero mean, so that we kind of make the limiting lattice to be a cubic unit cell that is scaled based on the number of atoms, and that turns out to be working very well. So I guess to summarize all the things that I mentioned, so we pay a lot of attention to really design this diffusion process very carefully, so that it fits the crystal structure, this specific modality very well, and then our result have shown that all these innovations, maybe there are around 5 to 6 of them, really all contributes to the performance model that really makes the model perform very well in generating new material.
Maybe just this is fascinating. This is the stuff that I geek out about because it's in our world. Maybe one last question about methodology before we talk about what it's actually achieve. You guys are Microsoft. You've arguably got more compute than anybody. So you have some luxuries that certainly we don't have in academia. Like oftentimes we just try something, and if it works, it's sort of good enough. And you know how deep the rabbit hole can be of hyperparameter tuning and architecture modeling and changes. How much, how optimized do you think this is? Is there a lot of room for further optimization, or have you sort of thrown the kitchen sink at it in terms of compute, and you feel like it's as good as it's going to be, and now it's time to start using it?
Yeah, I think this is a very, very good question. So I do believe one of the core advantage we have at Microsoft is that we have really a team of interdisciplinary researchers really kind of pushing this really, really hard. So I think it's not only about the compute, but it's also about really kind of trying all kinds of ideas and
I like that.
using the real kind of magic, right? Real evidence to see, okay, which works, which doesn't work, and iterate really fast using a very well-defined metric to guide your model development. So we think MatterGen is very optimized, like given the knowledge we have back then, which means basically, I think if you're doing diffusion model for materials, I think that it's pretty optimized. But there are lots of new algorithms, right, coming out, like flow matching, just coming out pretty recently, right? So that and all this introduces a different kind of a design knobs that
Okay.
I'm pretty
Yeah.
sure that you can still optimize it, and there are actually more and more models coming out in Europe, iClear, and all these ML conferences, and people trying all kinds of new ideas. So I can see definitely room for improvement also from model side. But I guess another point I want to make is that I think the data is really one of the key because one of the biggest jump we managed to get for model performance is really that we scale up the data size by 20 times, and that's one of the biggest improvement we see. So I kind of do kind of buy in this language model argument that that really so you can do a lot of things from the model side, but I think one of the key things that will make a difference is larger data and high quality data.
We'll get into the results of the paper, what you guys have actually tried to find, and if the goal is to find new materials, what types. And I ask that because you specifically have this conditioning capability. You have this inverse design where you can start with the property in mind. So tell us about the properties in mind that you had, and then how you actually found out whether or not you were able to discover new materials.
Oh yeah, that's a good question. So we in our paper we look at uh, like first there's different type of properties. For example, we tried to condition on atom chemical system, which is what atom type you have, and we tried a space group, and we tried different properties, which including electronic and magnetic and mechanical properties. And more specifically, we tried the band gap, and we tried the mechanical property, Bach modulus as a mechanical property, and we tried the magnetic density as a magnetic property. And so the reason we pick all these properties is because it's more because it's just available. There is a workflow out
Sure.
there that we can directly use rather than we think very carefully over, oh, we really want to find some materials. This is more like as a benchmark, right, to find out whether or not we can do property guided generation across a broad range of different tasks. And one of the key results we managed to show in the paper is that, okay, you can condition on a very extreme property like a very high magnetic density and or like super hard materials, and then you can shift the distribution, the general distribution, to a value that is very far away from the training data distribution, which could be top 1% or it could be top 0.1 percentile in the training data distribution, which is quite significant because in a lot of the materials design problems, you're looking for materials with extreme properties, right? You're looking for super hard materials. You're looking for materials with very high
Yeah, outliers.
density. Exactly. So, and then the ability for the model to do that is quite surprising to me actually when I first see the result. We actually managed to shift, for example, bulk modulus about 400 gigapascal because there are only maybe one or two data points over there in the training data. So that is one of the big achievements, and then from the model.
Yeah, you have this great figure where you show the distribution of the labeled data that it was used to train on, and then you show the distributions of structures and the properties that you're able to generate. And you can totally see they're almost totally different in terms of you being able to push those distributions not only towards a target and have that be kind of your mode for that distribution, but also towards those extremes. So it's very impressive. I feel like in a lot of generative models, the big struggle is how do you get away from the common distribution that you trained on. A lot of them end up just kind of collapsing towards the mode of the labeled data. So being able to make that shift and deliberately control it is huge.
Yeah, exactly. So that's also, to me, that's the biggest surprise that I got from this research. And that's why I'm also super excited about this capability.
Well, doing it is one thing. Like you could get your generative model to cook up all sorts of kooky things that have, these properties or whatever. But if the material doesn't exist, then it doesn't do you any good, right? If it's a fantasy material that's not thermodynamically stable, it does nothing for you. And so an important part of this paper, at least in my perspective, is that you've actually tried, and in some cases you've succeeded in making some materials and showing that it's the right phase. Now, I was a little surprised to see you did powder diffraction, just because anytime you find a new material, the real gold standard here is to do a single crystal. But then again, you did do a complicated oxide structure, and that's not easy to grow. And powder's pretty convincing. My solid state, chemistry friends might grumble a bit about it, but it's pretty convincing. The point to me, I guess the takeaway is like you did it. You actually showed that it can conditionally generate a new structure. That compound exists because you were able to make it. What gut feeling do you have in terms of how effective are the tools that we have for screening on stability? Because everyone always talks about energy from hole and things like that. And I don't know if that's a really good metric for actual thermodynamic stability, if I'm honest with you, especially if you're doing a machine learning prediction of it. What thoughts do you have about that?
Yeah, 100%. So I think that we really dived down, right, to really, because that's also one of the feedback we're getting from the reviewers when the paper is on the review. So that basically reviewer really want us to find a real material, things that real material. So we collaborated with our partner at Shenzhen Institute of Technology to really synthesize this material, tantalum chromium oxide, and so we show that the property of this material is within 20% of the conditional value that we target on, which is quite reasonable from an experimental point of view.
Was it higher or
And
lower?
it's lower. So the conditional value is 200 gigapascal, and the measured value is 169 gigapascal. But there is actually a lot of uh, details there, which is that because it's a powder, so therefore, if you so basically, if we kind of we measure it, right, we kind of get different values, but we are not sure if the because it could also be that you're usually always measuring lower than the actual value because the powder, the size of the powder is quite small. Therefore, there's if there's a moving beside the powders, you get a pretty low, you get a much lower value. So yeah, there's a lots of so therefore we think
Oh, this was
perhaps
like a bulk measurement. You're looking at like the geometric shape change to get the bulk modulus?
no, we're getting the real kind of particle. Yeah, we're trying to measure the particle, but the particle is quite small. So therefore, we kind of try to basically use something called nano indentation to
Oh,
really
I see.
measure the modules. Yeah.
So what you ought to do next is when we published a machine learning, it was a screening, not a generative tool, it was a screening, but we were
Mm.
after new super hard materials. And again, reviewer was like, you said you did it, but you never actually measured bulk modulus. So I naively was like, well, let's just measure bulk modulus, not knowing what a huge pain that is. The correct way to do it, well, the unambiguous way to do it is to do some sort of like diamond cell anvil, right?
Yeah.
So you load the thing and then you squeeze on it and you're looking how the lattice parameter shifts as you squeeze it. And from that relationship, you can curve fit it and get the bulk modulus. It's this whole ordeal. So
Mhm.
nano indentation is an approximation of that. Um,
Yep.
but I guess your takeaway is like, it's close enough, right? What we're
Yeah,
trying to
it's a
show you is that it's conditional and it looks like it's conditioned towards a high bulk modulus material.
exactly. So I guess what we're doing here is really just a very simple proof of concept and
Yeah.
trying to say, okay, because we think the bulk modules is maybe one of the easiest to measure, and then we try to kind of and also so we try to have at least one example to kind of think to show we can synthesize. And we would hope that because there is not fundamentally, there's no difference between different materials. So we hope this can translate to many other different kind of properties. And coming back to your question, which is that, okay, what is the, so how good it is, right, in terms of energy above the how, in terms of the synthesizing the real material. So what we actually did in the paper is that we kind of we actually generated a lot of materials at the very beginning. We generated maybe close to 10,000. I forgot the exact number. And then we tried all kinds of different calculations, including phonon calculations, including running molecular dynamic simulations to see if the structure will collapse, and many other things, and really to kind of filter out those candidates that are not stable. And then we also, I think that end up with maybe a list of around 50-ish, I forget the exact number. And then we worked with our partner really to look at them and trying to find them the ones that are more likely to be synthesized. And then we tried 4 materials, and then one of them is successful. So that is the approach that we've been
Very
taking.
cool.
In my own view, so this is one of the biggest bottleneck, right? Which really, okay, you can generating a lot of materials, but which one do you synthesize, right? And what is the precursors we'll be looking at?
Yeah, what's
And
the
then that
recipe is a whole nother question.
exactly. So
Even if you're convinced that it's stable, how do you make it? And with what starting
yeah,
materials? Like, yeah, I agree. That is a big problem.
yeah, exactly. So therefore, uh, in my view, one of the biggest area for the improvement of this model is first is that can you generate more synthesizable materials, right? So therefore, can you generate materials that are much easier to synthesize? And second is that how would you synthesize them? In my view, that's one of the areas that this is really a future area where this generative model can be further improved. Yeah.
All right, so I think this is a fantastic tool, and I'm sure it's going to continue to get better as data and algorithms improve. But I'm already wondering how this is maybe going to get incorporated to the broader suite of tools that Microsoft offers. You have anything you can say about that?
Oh yes, absolutely. So what Microsoft is doing is that Microsoft is creating something called Azure AI Foundry, which is a unified platform for hosting all kinds of AI models. It currently already hosting models like GPT-4, Llama, DeepSeek, and then we are also putting all the latest research from Microsoft research into part of the Azure AI Foundry called Azure AI Foundry Lab. And so one of our models, MatterSim, is already available at Azure Foundry Labs, and we are planning to put MatterGen as well on the Azure AI Foundry platform.
Yeah, we hope to have a future conversation about MatterSim. We've had people asking about that one for the show, so maybe stay tuned on that one. That would be great. One thing I've been excited about is, okay, these are available on the Microsoft platform materials. I'm excited to learn about this Azure AI Foundry. I'm also really excited to see that how much of this work is open source. You want to talk a bit about Microsoft's, sort of commitment to open sourcing and how far that's going to go? Because obviously you want to sell a product, and yet you've released some really great stuff so far.
Yes, so I think the reason we decided so first the MatterGen is fully open source. So we put both the training code and the inference code on GitHub. We also put our data on GitHub, and also we put the evaluation pipeline we have on GitHub. So everything is really fully open sourced for MatterGen. So the reason that we want to really open because we open source MatterGen is because we believe it's the early stage for Gen AI for begin to impacting materials design. So therefore, we really want all the community, right, to really try out these tools to see how does this work, right, for their own systems. And we want to learn from the
I
community
love it.
to see what are the limitations of these tools, right? What are the things that we could improve, further make these models more useful. That's why we are taking a very open approach for MatterGen here for the open sourcing.
So from my understanding, you have MatterGen, but then you also have MatterSim. Can you talk a little bit about maybe the differences here, and then how you might combine them to make something even better?
Yes, that's a great question. So, MatterSim, MatterGen is like generative model we've been talking about for a very long time, right? MatterSim is what we call a AI emulator, which basically it's a universal machine learning force field, but its goal is that you can simulate the materials properties much faster than quantum mechanical methods like DFT. So the way that we imagine how these models work together is really like a flywheel where you start with MatterGen, you begin. So let's say for a specific property like the super hard materials, right? So then you kind of first generate materials using MatterGen, and then you simulate the properties using MatterSim, and then you once you get these labels, right, and then you can use the data to further fine tune MatterGen, and then iteratively you can basically discover better materials. And both MatterGen and MatterSim, they are pretty general models, right? They can be used for many different type of applications. Then we hope that these two models can function as some of the foundational layers for people to use AI to discover all type of different materials.
Okay, Tian, this conversation's been fantastic. This tool is clearly really cool. I just have one last question for you. And I've had this about several big tech companies that are getting involved in materials, which is help me understand why Microsoft is doing something why you're investing such resources in material science. I mean, I'm delighted. Don't stop. But I'm just curious for your average listener who just uses your software or your, computers and things like that. Why are they doing this? Can you help us understand and what the opportunity is?
Yeah, I think what Microsoft believes is that AI is one of the biggest factors, right? So that will basically transform the entire society in the coming decade, right? So and our CEO Satya Nadella calls it a big paradigm shift, right? In the technological revolution. So we believe that scientific discovery is one of the most profound areas where AI can make impact, right? Because and that's probably also one of the hardest areas, but it's at least in terms of the real world impact, is one of the biggest areas AI can make. So that's why we are created. So the organization is called Microsoft Research AI for Science, was specifically created for this mission, which is to create AI tools to enable breakthroughs in scientific discovery. So more specifically, materials is obviously one of the very big areas in scientific discovery. A lot of the biggest societal challenges our society facing today, they are really bottlenecked by finding a good material, right? By the batteries, by the catalysis. So what we're really trying to do is that we hope to create the world's best AI tools to empower all the companies and also researchers around the world to design the best materials.
The world's best AI tools for the world's best materials. That's a great place to end it. Tian, this has been such an awesome conversation. Thanks for joining us. Across the time difference, you're in the UK, so we appreciate you making time for us. And I can't wait to see what you've done next, right? This is the sort of magnum opus. Are you going to outdo yourself next time around? I can't wait to see what it is.
Thank you. It's so nice to be in a podcast, and Taylor and Andrew, so nice to be speaking with you. Yeah, looking forward to our future interactions.
Okay, well, hopefully we will see you soon.
Absolutely.
Bye. All right, today's episode is brought to us by the American Ceramic Society. Not the first time they've been on the show, is it, Andrew?
No, they've been on quite a few. They helped us put together a great series early on in our podcasting career.
Definite friends of the podcast.
Different ceramic materials.
They've got a cool new website, right? And to call it a website is not doing it justice. The American Ceramic Society, or ACER's bulletin, is pretty rad. It's sort of like a research article / newsletter / industry guide all rolled into one, and they've updated it and it's better than ever. What do we find there, Andrew?
Yeah, all sorts of stuff. I mean, if we look at their most recent issue for April, they've got a great article headlining about how to prepare for an AI-empowered workforce. Things like reskilling and upskilling, the ways in which the ceramics and glass industry is changing with the advent of new computational tools.
Yeah, if you're in this industry and you're not already using AI as a tool, I hope you'll check it out because I certainly think it's important. Now, we love Acers. And there's something that they are doing to show their love for you, our listeners. They're giving you free stuff. In fact, if you go to ceramics.org/materialism, they have a special landing page just for our listeners. And if you go there, first it'll keep track so they know that you came from us, which we would appreciate, but it'll also give you some free stuff. For example, they'll give you a free 1-year membership to the American Ceramic Society, which is so cool. And with that, you get access, for example, to the Acer's Bulletin. They've got 100 years worth of issues there, which is pretty awesome. But you get other cool stuff. Your membership gets you discounted registration to meetings, products, courses. We're going to have a lot more to say about that. So check it out. If you haven't gone already, go to ceramics.org/materialism and unlock the full access to the bulletin with your free American Ceramic Society membership.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialism podcast on Instagram, or pretty much everywhere you want to find us. We are out there and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.